So since the nuclear density is roughly constant, we can treat the neutrons and protons that make up a nucleus like the molecules of water in a liquid, and it will make up an incompressible liquid. The individual protons and neutrons move around freely, but they're confined to be within that volume, and that volume can't shrink. They can't get too far away from each other, but they're not locked into a rigid position. When we do that, we can then use that to come up with a formula for the mass of a nucleus, a mass of an atom, really. And it's called the semi-empirical mass formula. And that's because the various terms, we understand why they happen, but the exact values we use are either fit the data on nuclei and atoms and isotopes that we have, or come from other means. So this semi-empirical mass formula has 6 terms. The first, and so here we have the mass is a function of number of protons, z, and the total number of atoms. Often I'm going to interpret this with an n, and where n is just a minus z. So I'll use that throughout. So the first term is just the basic. We count up all the mass. If we have z protons and n neutrons, we just add up all their masses, the masses of those, right? So to give the mass, we have to remember also that there are the atomic number versus number of electrons as well. So we just add up what we think all the components going into the atom are. The number of protons, the number of neutrons, and the number of electrons, and we add that up. It turns out that that will always be more than or equal to, but usually more than the sum of the parts. Only for hydrogen atom is it the same. So the first term that we add to it is called the volume term, and I give that here. And basically we say that the neutrons and protons stick to each other with a certain amount of energy. And that energy takes away from the total mass of the result because it's a binding energy. That's the primary binding energy of the particles. And each particle that you add adds a little bit more binding energy. And so this energy is the binding energy. It reduces the mass. And it has some factor A1 times the number of particles that you have, the number of nucleons, neutrons, or protons that you have. And so basically each neutron or proton you add, we say, in this case, subtracts from the mass of the total by about 15.5 grams, 15.6 grams, MeV, excuse me, in this case. So we're adding in mostly GeV at a time up here, and then for each one we subtract off 1.5% of that for adding it in, and that just grows with the number of particles you have because you're binding more. The second term, it's called the surface term, is because if you have a sphere of protons and neutrons all bunched around, the protons and neutrons at the edge only get attracted to from one side, and therefore they have a little less binding energy attributed to them as the others. And so the ones at the edge go as, the surface area of the sphere, which will go as the square of the radius, and the radius is proportional to 1/3 the number. So the 1/3 of the number of particles squared is a to the 2/3. This gives the surface area of the nucleus, and then we multiply it by this factor A2, which is 16.4. It's not surprising that these two numbers are of the same order, because when A is 1, we expect there to be no effect either from the surface, which is everything, nor from the volume. And so they have to cancel when A is 1, and we just get the mass of the proton in that case. So then the third term gives the fact that, of course, of the neutrons and protons in a nucleus, the protons repel each other with the Coulomb force between two same size charged particles. And for each pair of protons in the nucleus, there's a contribution. So we have to count up the number of pairs of neutrons. And so for each starting proton, there are z minus 1 remaining protons. So this gives the number of protons total. And then we have to divide by the radius. So we notice this is multiplied by a number that's much smaller than the volume terms. This factor represents something of the ratio of the strong force, the nuclear force between protons and neutrons, and the electromagnetic force. You see that it is 20 to 30 times larger force. Finally, the last two terms account for factors that we see in the chart of nuclides. We notice that the number of protons and the number of neutrons is roughly the same, and so we have to account for the fact that why should that be? Certainly you could have 1 proton and 100 neutrons, but that is not in fact bound, and why is that not the case? So we want a term that's proportional to the difference between the number of neutrons and protons, and we want it to be squared because we want it to be go on either way against that. So in the chart of nuclides, if we go along the diagonal line that represents the isobars, this factor gives us a quadratic effect on the binding energy. And it has also a magnitude of the curvature is about 23.3. The last factor accounts for the fact that the nucleus likes to have all the spins cancel. And we haven't talked too much about the spins of the proton and neutron. They're both spin 1/2 particles, but they add up to try to give very small nuclei. And in fact, if you have even number of neutrons and an even number of protons, those are always spin 0. And to account for this, and the fact that even numbers are preferred, you add a factor if both the number of neutrons and protons are odd. We add that detracts from the binding energy. And if they're both even, we add to it. And if the number of neutrons is even and the number of protons is odd, or the other way around, there's no effect. So those are the 6 terms in the semi-empirical mass formula. I wrote a program to calculate how this affects on the function of z, and I'll post that on the website. But the examples are here. So if we just look at the binding energy per nucleon, we're taking the sum of these terms after the first one. So the binding energy doesn't account for just the adding, but the reduction from that. And then we're also dividing by A. So the first term, the binding energy, is just the binding energy per nucleon that we add. And that was this 15.6 number. And it doesn't depend on what A is because we've divided that out. And so that's a constant binding energy per nucleon for the volume term. If we add in the surface term to that, we get this factor coming down. And so things are less bound because of the surface term. Then if we add in the Coulomb repulsion, we get a larger effect going to larger Z, which is larger A, because we have more pairs. And we now start to see that this peak starts to develop because of the proton repulsion in the nucleus, which is why iron is the most stable, and that when you get up to uranium and elements with lots and lots of both protons and neutrons, they start to become less stable. Finally, the asymmetry term adds a little bit to that as the protons and neutrons, you start to have more neutrons to start to become, to make the nucleus more bound to overcome the Coulomb potential. The asymmetry term and the spin term I illustrate here by plotting the binding energies for A equals 102. So this is an isobar protection. The number of neutrons plus the number of protons is 102, and show the fact that as you move away from equal number of neutrons and protons, you get an effect that gives you this quadratic dependency. The blue points don't have the spin effect, and this is just a quadratic effect based on which it is. And so in this case, you would predict that ruthenium would be the most bound element with a atomic mass of 102 U. And then as you go to the side, rhenium and palladium and silver and cadmium become less bound with this number of nucleons. And likewise, if you go to the other side, you become less bound. That's why there's a trough of stability in the middle of our chart of nuclides. However, the even-odd effect shows, so A102 is even, so you can have an even number of neutrons and protons as you do in ruthenium, and it's bound, and it's a little bit less, or it's a little bit more bound than it would have been without the even-odd effect. But on either side, rhenium and technetium have an odd number of neutrons and protons to make up the even total, and they move up from this line, and so they're less bound. And in some cases, the reason you get many bound states with even is that in this case you see molybdenum is almost as strongly bound as technetium, and there's no way to go over the hump there, if there were a hump, and in some cases there is. And that gives rise to the particular form of the chart of the nuclides, where you have a lot of isotopes and isotones with even numbers and few with odd numbers of neutrons or protons in either case.